Okay, so the graphical representation of forms. Suppose, so we have some particular A, P, and we have a corresponding form of A. Now, the form of A has to inform P, or AP. The form of A has to inform the particular. Okay. Then let's say we have the form of informing. Fi, I said F in the earlier video. Fi has the form of informing. So this has to inform A of F so that A of F can inform A of P. That's fine for Plato, where the forms are eternal and we don't abstract from them. We abstract then from math. We mathematize them, I suppose, but they're eternal. They're always there. They inform the particular. But for Aristotle, you have the particular, from which we abstract the form. So it has to go backwards. But that means in order for the particular then to basically inform the form, according to Aristotle, I guess that's one way of saying it, it has to have the property of informing. So it has to inform both. Furthermore, I'd say the form of informing. No, actually, I retract that entirely. There's the form of informing, which informs the form to inform the particular. This will inform all other forms. Then you have the form of abstraction. The form of abstraction, which informs the particular, from which we get back to the form. Okay, so from which we get to the form. I'll use double arrows for that, I guess. So from the abstraction, we get to here. Okay. Now, graphically, I would represent this as such. Actually, I'll use capital A for the form of A, and I'll use lowercase a for the particular. All right. Okay. This is fine. That's what this is. Now, there seems to be this hierarchy. All particulars will be down here and correspond to this realm of forms here. Okay, so you'll have another particular, say B, and you have B. But then for B, you're going to have informing so that it can inform the particular. And for A, you're going to have, or B, sorry, you're then also going to have the form of abstraction to correspond to, well, B. So I think you have these two forms that are kind of like an Uber form, effectively. So I guess we'll have the realm of particulars, and then the realm of forms, and I guess the realm of the Uber form. I really don't know any better way to say it. Okay. So then what we also get from this, in graph theory, if we were to represent this, I'm actually going to start with the particular form. So we have graphically, two nodes B and A for the particulars, which correspond to two other nodes, B and A of the form, which correspond to another node, which is the form of informing. But you also get the form of abstraction down here. The form of abstraction which informs both. So I'm just going to put it down here to keep it simple. But this is a cycle. The MSRG of the cycle cannot be determined. Or rather, there are, in this case, 1, 2, 3, 4, 6 nodes, but Z is 0. MSR of the graph is less than or equal to n minus z. Consequently, it's less than or equal to 6, basically as many nodes as you have. This is no good. And this is why I think there is such thing as equivalent forms. Okay, suppose instead of form of abstraction, there's only the form of informing and the form of abstraction, but instead of the form of abstraction informing the particulars, it informs the form, like I was saying earlier in the other video. What if you do this? Then, this is no longer the case, and you have this. This is a tree graph. That's fine. The nodes, again, is 6, but Z is going to be 1. I believe. Z is done combinatorially by determining, well, actually, let's actually go over that. Suppose you have the graph this. N is 4. Z is determined combinatorially by the color game. So you color in several nodes or one node arbitrarily, and you continue to color in adjacent nodes so long as you don't come to a node where there are two appended vertices. So you color in one node here, you can color in the next, and subsequently, that's as many as you can do, because you can't color in either one of these because it has two corresponding vertices. But there's only the one, so you can come here. That's it. So Z would be 2. It is the minimum number. You can start somewhere else. Okay? Let's say you started on this one. Well, you can't color in anything else. So Z is 1. If you did it that way. Start here. Well, you have 3. You can't do it. Z is 1 here. Z is 1. Here Z is 2. So Z is just, well, we'll see. Okay. So if I have that figure, the MSR of G, MSRG, is less than or equal to n minus Z. So it's less than or equal to either 4 minus 2, which is 2, or 4 minus 4, which is 1. 4 minus 3, which is 1. 4 minus 1, which is 3. So it's either going to be 2 or less than or equal to 2 or 3. Well, since it's an upper bound, you want the smallest of the values, unless for whatever reason you want the biggest possible upper bound. So for our purposes, we want two. Yeah, two, right? So you only need 2 dimensions to the MSR, the minimum semi-definite rank of graph G then is less than or equal to 2. Turns out it is. Basically, it's the MSRG is the number of dimensions required to represent the graph. Well, it's 2. This is a 2-dimensional graph. I have this height dimension, length dimension, you need 2. I had 3 as another possible value. It could be 3. I can pull this out of the board, and there you have 3 dimensions. It'd be height here, then across this way, and then out of the board. From here, this node would come out of the board, so you have 3 dimensions. It could be, but I only need 2 to represent it. I can't do it in 1 because of that cyclic component of the graph. So I can't do it in 1. So in this case, MSRG is 2. It's less than 3, but it is, in this case, no less than 2. So it's a very simple one. The forms, however, are, possibly infinitely more complex. Suppose you have this simple model of forms. Okay. N is 6 in this case. You have 6 nodes, but N in the real world would be the sum of all of the particulars and forms. Here you have the particulars, the forms. Actually, I'm doing it over here. You have the particulars, the forms, and the uber forms. Okay. So you'd count all the nodes in the graph, but that's going to go through all 3 layers of, the formal cosmos, I guess we can call it. Okay, fine. So make this neat. In this case, N is 6. Z we don't know yet, and so we don't know the MSR of the graph. Okay. Now, what is Z? If I color this in, I can color this one and this one. So that's 3. It could be 3. If I color this, I'm going to do the same thing. 1, 2, 3. Then I can't color anymore because I have 2 attached vertices. Okay, so it's 3. I can color this one in, and then it's 1. I can color this one in, and it's 1. Here, 1. Here, I can color this or this, so it's 2. 1, 2, or 3. That's my Z value. Plug it in. I have 6 minus either the 1, 2, or 3. So that's either going to be 5, 4, or 3. So it needs, it's less than or equal to, I'm going to go with the smallest of those values, so 3. MSR of G is less than or equal to 3. Look, we only need 2 dimensions to represent this. I could pull this out and it would be 3. But I only need 2, which is less than 3. So in this case, it's not going to be equal, but okay. Okay, so that's fine. That's just the tree graph. Now, here's where I think looking at it graphically kind of helps the theory. You can have multiple particulars correspond to a single universal. In this model, suppose you have the universal of red and, well, actually, white and blue. Okay. These are your universals. Okay. Well, what has red, white, and blue? A lot of world flags do. So let's say there is the, well, I guess the obvious example is obviously the flag of Norway. So so if you have any flag, the Union Jack, Norway, I think it's Norway, the American flag, you have a lot of flags have the French flag. A lot of flags have these three colors. So you have multiple particulars of all the flags. Union Jack, Norway, America, France, and there's a lot more. All of these have those universals in them. And so you see all of the possible combinations now that can arise from, or sorry, I doubled up there. Yes, no. You have all these possible combinations that arise from this. What does that mean? Well, let's look at a very simple example. Let's say, to my knowledge, I could have actually kept those. Red and white. Those are my universals. To my knowledge, there's only one flag that has only red and white, and that is the flag of Poland. Okay, so you have the Polish flag. And let's say that's the only particular that has red and white. It's obviously not, but let's say it is. Polish flag, particular, red and white, corresponds to both. Now, the Albanian flag has red and black. Okay, Albania. So the Albanian flag and the Polish flag have red in common. All of these have the form of informing, which is always going to have the form of abstraction. And basically because, that's what I kind of wanted to say earlier, you have the form of informing and the form of abstraction. Because they're equal forms, this is it. They're the same thing. They inform each other. I think that's going to have to be an axiom in the system. If they're an equal form, they inform each other, so there is no infinite regression. I think that's just going to have to be what it is. Whether or not I accept that, I don't know. So let's just play with it. So let's just keep this model for now. Okay, fine. So, okay. Okay, yeah, let's just leave that. Let's do whatever. Well, what happens if we don't even have that? That's interesting. Okay, basically, it's a big cycle. You can't get anything. You'll have, 6 nodes again, and you're not going to have any z value because you have here, that's 1, or z will be 1. Here, 1, 1, 1, 1, 1. Anywhere you go, z is 1. And so you need 5 dimensions. So MSRG is now less than or equal to 5. 6 nodes and a z value of 1 is less than or equal to 5. That doesn't tell you much. I'm doing it in 2 dimensions, which is less than 5. So it's within the parameters, but at this point it becomes a fairly useless number. The whole reason why I had started to look at it in the first place is, well, actually, let's do that. Let's keep this. The reason I started to look at it in the first place is because what can this number tell you? It says that this can be expressed in 5 dimensions. It can be expressed as a 5-dimensional graph. So, I guess then the question becomes, what significance does that have for the theory of forms? What significance does that have? And that's where I'm starting to get a little stumped. But I can't quite shake the notion yet because, well, using math to discover the nature of the forms is very Platonic, and that is very appealing to me, so there's that. But I can't quite shake this because this isn't reality. This is an example. This isn't necessarily the case. For all we know, this could be. Because keep in mind, you can have all the nodes you want in your graph, and they can create this most elaborate structure in the universe. Oops. Okay, they can have all that. They can have whatever you want. You can have what is effectively one big cyclical graph. You only need one node to bring down that zero forcing value to 2 now. And you only need one more. Well, I can color in these 2. Oops. I can color in these 2. And that's a shame because that was, again, a very sublime piece of chalk. I really did like that. Anyway, so you have this. I'm actually kind of upset about that. It took me a while to find a nice piece of chalk like that. Okay, so you have this sublime. You have the sublime piece of chalk and this sublime graph. Really, but you have these 2 values here, so now it's 4. So I color in these 2, and I go to these 2. That gives me 4. So z is 4. Suppose I had another one. Or one more attached to that. That's 4, 5, 6, 7. Z is 7. Okay, so now suppose, I'll draw this a little better. Suppose now I had this. Well, z is 7, but n is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Hey, that's not too bad. It's better than if it were all cyclical, in which case z is 1, right? So it's not too bad. It only takes 1 to really bring it down. And this is where I'm kind of intrigued. As a physicist, I accept there are a finite number of things in this universe. Furthermore, I'll even go so far as to apply this to Bunge's system of emergence and Smolin's idea of black hole baby universes. You'll see, I hope you'll see where these all fit together. So if you have a finite universe and a finite number of things, okay, if you have a finite universe with a finite number of things, then it follows there are a finite number of particulars, as many as there may be. Okay, as many as there may be, there are a finite number of them. So here I have 2, 4, 6, 8, 10, 12 apostles, 12 particulars. Okay. So you have 12 particulars, right? And even if they all corresponded to one form, that is the form of whatever the particular they are, I think I counted right, 2. Yeah. So if you have, each one corresponds to one of its own. So, I have an apple, a banana, a peach, a pear, a walnut, what have you. It's going to correspond to the form of apple, the banana, the peach, the pear, the walnut, whatever. Okay. That's what it's going to do, at the very least. All of these are going to correspond, again, at the very least, to the form of informing. And all these could even correspond to the form of abstraction. Okay. Whatever, all those correspond to the form of abstraction. That's fine. But here's what I'm kind of thinking about. No, I don't like that. Nope. I rejected that earlier, and I'm still going to reject it. The form of abstraction, superior form of informing. But they're equivalent forms, right? So it's not actually superior, but they're equivalent forms. So be a form of informing is to be a form of abstraction, I guess. Right, so if you have the form of abstraction, the form of informing is connected to it. So it informs the form of abstracting. So the form of abstracting has the form of informing. And so the form of, right, so, okay. That's kind of the whole thing here. If you have a particular, so if you have apple and red and apple, you have the form of red and the form of apple in a particular red apple, which has both of these forms. So you have the red apple, the particular red apple, which corresponds to both of these forms. So it has the property being red and it has the property being an apple. This has the form of informing, both of them, because they informed this. They have the property of the form. That's the thing. The particular has the property of the form to which it corresponds. So I'm not going to try to, no, that's that. Yeah, so the particular has the property of the form in which to which it corresponds. So the form of informing. So if we are allowed to abstract from the particular the form, well, we were just able to abstract from this form the form of informing. So this has to have the form of abstraction. So this has to have the form of abstraction. But if this form informs this with its properties, we only need this. This is the only thing that has to happen. So now, this works, because the form of abstraction informs the form of informing. So now this effectively becomes the form of informing and abstraction. They're equivalent forms. So, but it's still a form, so it informs these other forms with its properties, namely of information and abstraction, which go forth to inform this. And because this has, so now this would have to have the form of red, the form of apple, and the form, this is a particular, but that doesn't mean anything, it's just an extension of the theory. I think there's the forms and the particulars, and the forms and the particulars are merely this dichotomy we've assigned to entities. These are metaphysical entities, these are physical entities, and that's the only distinction between them. One happens to be corporeal, and the other happens to be incorporeal. And so this still is a form in a very physical sense. Hence, things have form and dimension, extension. Okay, maybe that's a bit of a stretch, but bear with me. It still has the form of red, it has the form of apple, but this has the form of informing, and this has the form of informing, which had the form of abstraction, so these also have the form of abstraction. So these have the form of informing, the form of being red, and the form of abstraction. This is the form of informing, the form of apple, and the form of abstraction. So this has the form of being a red apple, and information and abstraction. There's nothing for this to inform. So that's merely the end of it. That just happens to be the nature of the physical realm, I guess, of the graph, this bottom layer of the graph. There's nothing below it. There's nothing for it to inform. It is the smallest of the small. It's as far as it gets. And yeah, you can break this apart into subatomic particles, whatever, and I'll do that. And that becomes the absolute bottom, the end of the line. It doesn't get any smaller than that. You have Planck volumes, and so now there's only so many particulars of extension because you can only have so many unit volumes. There's now, particulars of time because you have Planck time, and so there's this quantized discrete unit of time, of space, of measurement of all these different values, and so there's now finite particulars that correspond to extension in time or space. And so the red apple would not necessarily inform that, but they're all particulars, so they all do this. So you have eventually, let's say, the proton. Okay. You have the form of the proton, then, which informs this, which comes from here. That's fine, and this just happens to be composed of the red apple. But I'm not going to say that it informs the red apple or anything such, because it's a particular. Because it's in the material realm, I don't think it informs anything else that is of matter. It may comprise it, it may compose it, it may interact with it, but it's not going to inform it in any metaphysical sense. Effectively, once you jump across this barrier, that's it. There's only relation, there is no longer information. It may have the property of informing, but only because it has the property of abstraction and vice versa. So it has the property of abstracting, it has the property of informing, but only as much as it informs the form, namely, we abstract to the form. It's the same thing. It's kind of like, is the chalk on top of the ledge, or is it next to the ledge? Well, from looking at it right side up, it's on top of the ledge. But if I turn my worldview 90 degrees, it's next to the ledge. Okay. And so you only need to have this. Could it correspond to the particulars? Could it correspond to every form and every particular? Or maybe only the particulars? Yeah, it could. But if it corresponds to all the particulars, then it's going to correspond to all the particulars, and you get this, this what is now basically just this cyclical graph, because that's not going to be there. It's down here now, corresponding to all the particulars. So you could have that in theory, but I don't think that's the best approach to do it. I don't think that's how the graph, how the theory should represent the reality. I think it's kind of like string theory. Before Edward Witten came along, you had 5 theories saying the same thing, but with different perspectives. And so you unified them with this new M theory. And I think this is kind of the same thing. You can put it down here and correspond to all the particulars. But it's a different theory, and you have to rework it. But it's the same thing as putting it up here. It gets the same job done, it describes the same theory, but this is kind of a unifying theory. It gets you the same end. That was just a different way of looking at it. I'm looking at it through this theory of MSRG as opposed to Platonic intuition, I guess we could call it, kind of just intuiting metaphysically what the case may be. So this is FA. Okay, fine. So you have the form of abstraction, the form of intuition, which we've already established is what I'm going to be calling an equivalent form. And so you only need this relation. Look at it like nature, things tend towards the lowest energy state. They don't waste energy. Look at it kind of like that. If you had it down here, it's a waste of energy to create bonds with all of the, all of the particulars in the entirety of existence. It's much easier to simply embed yourself into the form of information, and then go from there. It's much easier. It just makes more sense. It's easier to do. It requires less energy if there was any energy involved. So it kind of follows these same naturalistic principles of tending towards the lowest state of energy. Okay, just as an interesting comparison. It also makes more sense. It furthermore allows you to mathematize the system. Because now it's a tree graph. Even if there's some corresponding particular, or maybe even a form that grows this, and you get this new, this cyclical element right here. Okay, so let's just simplify this. So let's simplify it with just, 2. Okay, so you have those, and then you can say you have this. Sorry, let's do 3. Okay, and you get this, you get these, and maybe you have some other form, or maybe a particular, I don't know, and you get this, you get something like this. This now becomes your graph. Well, despite this circular part of that graph, you still have 1, 2, fine. But hey, look, 1, 2, 3. Now z becomes 3. Very good. So if you haven't noticed now, the trend is you always want the largest z to get the smallest MSRG. So, in this, you get 3, 6, 9 is n, so the MSR of the graph is less than 9 minus, in this case, 3. Oh, very good, 6. Okay. And you never know. There could be a chain like this, in which case you're going to have what? Sorry. I'm trying to think. How many do I have? 9, 10, 11. So 12. Let's say I have 12. That 12 minus the 1, 2, 3, 4, 5, 6. I think you're always going to get 6. Conjecture. I think that you're always going to get, if you just keep adding the chain, you're always going to get 6. You're kind of stuck with 6. Unless you've had a different chain. If you had this, well, now it becomes 1, 2, 3, 4, 5. But you could start here and color in those 2. or this 3 or whatever. So you're going to get, you can color in this one and then this one. Fine. So that's 2, 3, 4, 5, 6, 7, 8. Well, that's 8. Oops. So now this z becomes 8. And your n is, what do we say, 12, 13? All right, so yeah. So it depends. And now you brought it down by 1, 5, by adding this. And similarly, now it's 4. Now it's going to be 3. Oh, okay. Your MSRG, is going to be 3. I think that's going to be right. If you just keep adding 1, you're going to add 1 to the number of nodes every time. So we had 13, this is going to be 15. But you're also adding in 2. So it won't really change in that case. It'll still be 5. Fine. Okay. Oh, yeah. So whatever. You can add them for every node you're going to get. So there are going to be limits or whatever. But that's the beauty of the thing, is you get an absolute then. Combinatorially, you can get a minimum of the maximum, and it will always be that. For instance, this will always be 5. It will never be any, you will never need any more than 5, ever. No matter what you do to this graph, so as long as you only have this one cycle. If you had another cycle, then that's a problem. Then it'll bring down that z value, and it'll bring up the node value, and so you'll get a greater MSRG. But still, it allows you to mathematize the dimensionality of the graph. It allows you to effectively mathematize the dimensionality of the forms and the particulars. So what is the dimensional representation of the universe? I'm going to go out on a limb here and hypothesize less than 5, less than or equal to 5. Well, because I don't even know if this is necessarily ever going to be the case. Because I think eventually you're just going to, you might have, branches off of these things, but eventually you're just going to get down to, whatever. And maybe you'll have circles within that, but now, it depends. But at least now you have a theoretical way to compute the dimensionality of this Platonic formal cosmos. Granted, it requires a certain series of combinatorics, but even then we can get a good estimate. So now let's try to mathematize an estimate. Suppose we have then a very simplistic thing. So you're always going to have the form of abstraction and the form of informing, always, from which the rest of the forms branch out. So let's say you have the form of red, white, I guess I'll stick with the flag thing. I don't know why I like red and white so much. I don't know. I do like pink and orange and whatever. Okay, so that's that. So okay. Okay. This is fine. So then these are your forms. These are the Überformen, I guess we can call it. German, so it has to be one word. Überformen. It's plural, so it's die Überformen. Whatever. So you have the Überforms. And then you have the forms. Formen. Okay, fine. Then you have the particulars. Let's use, say, the Union Jack. So you have the Union Jack, the British flag. Okay. Fine. Look. Now, this is a problem. Okay, but fine. So right now, this isn't so great because you have 6 nodes, and your z value is going to be 2. Your z value is going to be 2. Your MSRG is less than or equal to 4. Okay. And that's not so great. Can we improve this? Yeah. How? Well, let's continue atomizing our world. The flag, there are material flags. There are many of them, so you have many particular Union Jacks. Which kind of complicates things. You have many different Union Jacks in particular, and so for all of those, you have to represent, they all correspond to red, white, and blue, and flag, and a bunch of other stuff, but just simply. This one corresponds to red and white and blue. This one corresponds to red and white and blue. This one corresponds to red and white and blue. Here's the problem. I cannot do this in 2 dimensions because I have crossing vectors. If I were to represent this in 2 dimensions, this is a new node. Well, to what form or particular does this correspond? Maybe it does, maybe it doesn't. I don't think it does. So let's just say it doesn't. How can you do this? Well, I can represent it in 2 dimensions with, say, this middle one. Okay. That's fine. What about these 2? Well, I have to now go into 3 dimensions. But I can do many in 3 different dimensions. I can have one flag represented. Schools, especially institutions of higher education, they really need boards that like come out, so you can kind of get the whole axis thing going and start actually drawing on this board and project 3-dimensional. There's an idea for it. But what you can do is you can take this, instead of drawing it on the board, draw it out here. So you have U, okay, and this will correspond to the red, white, and blue, but this is in 3 dimensions. But there's no crossing vertices. It's out here. And the same thing, but it's going to go into the board on the other side of the graph. But then I could have one, as opposed to, here at 90 degrees, I could have one up here. I could have one down here. I can have several along this arc right here. And the whole circle around the board. I can have them anywhere along here, and there will never be a crossing vertex. Edge. There will never be a crossing edge. So that's that. So you can do this, but again, you might need 3 dimensions, which still is within our original bounds. Even if you had the 3, right? You have the 3, okay, and then they all correspond. Whatever. So you're going to have 1, 2, 3, 4, 5, 6, 7, 8 nodes. You have 8 nodes, and you're consequently going to have still z is 2. Because all these are going to be cycles. So, well, that doesn't really help. Now it's less than 6. Great. But it's still within the bounds. You see, so but you need to raise it into 3 dimensions. Depending on how many more, you might need more. So, we'll see. But for simplicity's sake, let's stick with the one Union Jack that has the colors of red, white, and blue. What is it composed of, I should say. Color. Okay, but what's the color? Well, first of all, fabric, or whatever. So paint and fabric, dyes, what have you, which are composed of molecules. So whatever molecule, we're just going to use one, just to simplify the example. Actually, there are going to be several. Molecule 1, molecule 2, which are comprised of several atoms. A1, I'm just going to use numbers. A1, 2, 3 and 4. They're all different atoms. And you're going to have what? The atoms are then composed of subatomic particles. 1, 2, 3, 4, 5, 6, 7, and 8, etc., etc., etc. But okay, so it's just going to keep going down. But you're going to see fundamentally it's a tree graph. Some may have, more than whatever. But it's still just going to be a tree graph. But that's fine. I have 1, 2, 3, 4. Okay, I have 8. I have 8 things I can color in at the bottom, and then that's it. Oh, that's really cool. Because now it does not matter what happens in the middle. I will always have, at the end of the day, a tree graph. I'll always have a tree graph, so as long as there's more than one particle that composes any given thing, which is true, you're always going to have a tree graph with at least 2 limbs to the thing of the next order of magnitude, right? So a molecule, there's no molecule with one atom, and there's no atom with one particle, and there's no one particle with one quark, and no one quark with no one strand. Okay, well there is that, but whatever. That's easy to figure out from there. So that's fine. So eventually you're going to get down to the number of particles you have and their subatomic constituents. These are all, so you can actually now begin to enumerate all of the particles, all of the particulars, because it doesn't matter now. You can have all these cycles within this thing and whatever. You have the molecule that has blue, you have the flag that has blue, you have the molecule that is blue, you have all this stuff. You can have all these cycles in the middle, and it doesn't matter, because at the end of the day, I can only color in, say, these bottom particulars, and I will never be able to color in the one on top of it, because this goes to here, so I can get that. So 1, 2. Actually, that's all you do. Get 1, 2, 1. Well, that's already colored, and that's it. So you'd have 1, 2, 3, 4, 5, 6, 7, 8, and you have 1, 2, 3, 4. So you're always going to have the sum of the bottom particulars and then all the subsequent things, whatever. So now, this is particle physics. This is just a hierarchy of the Standard Model. So you have the sum, ultimately, let's say, just again for simplicity's sake, quarks are the bottom. Okay, you have, let's say, 10 quarks in the whole universe, right? Or, well, let's say you have 8 quarks in the whole universe. Quark 1, 2, 3, 4, 5, 6, 7, and 8. Actually, 9. Let's say there were only 9 quarks in the whole universe, because you have to have 3 quarks to compose the baryon. Okay, so now let's say you have 2 sigma baryons and a delta baryon. All right, so let's say you have sigma plus, which has these 3, and these 3 compose another sigma, null, whatever, and then these 3, which comprise the delta baryon, which actually is always capitalized, isn't it? Okay, so then you have these which comprise the delta baryon. Okay, and whatever. And then these 3 baryons are going to be, whatever. Maybe, one's a proton. At this point, you're at the levels of protons, which will now always be higher ordered particles, so atoms, things like this. So this is it. If you know all the quarks, you figure out the baryons. If you know all of the superstrings, you'll figure out all the quarks. That's it. Each quark has one superstring, S1, 2, 3, 4, 5, etc. Each quark has one superstring. So even if superstrings are the basis of reality, the basis of the fabric of the material realm, you can still do the math. Because let's say now we're, these are protons. So let's say you have these 3 baryons, whatever they are, come together to create some proton or neutron, whatever. I don't know. Actually, I guess or quarks. Sorry, this would be the proton. These 3 come together to create an atom. An atom, right? That's fine. Because now all the atoms, this is it. Then you get to molecules, and then you get to stuff. So you're always going to have this tree. And because you have the tree, there's this pattern that is necessarily the case. We can guess that there are about 10 to the 80th atoms on average. So we can get this 10 to the 80th atoms or 10 to the 80th whatever. And there are estimates as to how many protons there are, which I can't remember. Let's just do 10 to the 100, okay? So there's a Google protons. Oh, great. That's all I need. Because I can add these. For every quark, there's one string. Yeah, and then there's also electrons too. So fine, actually, atoms, rows of electrons. So there's also going to be the electrons floating around here, which have one string. So that's easy, right? So for every atom, there's one electron. But you see, if there's 10 to the 80th atoms, then there's 10 to the, well, I guess I can't do that either, but it's negligible. There's then about 10 to the 80th electrons. Even if you have 100 electrons per atom, this plus, it's just not negligible. Fine, 10 to the 81st. Okay, big deal. It's like this plus 100 electrons for every one atom. Okay, it's still not a huge number. It's not a big difference. So let's just say 10 to the 81st, whatever. These are just estimate numbers. Fine. Okay, well then there's going to be for every one electron, one string. So there's 10 to the 81st strings. Just for that. Okay, but there's 10 atoms, 10 to the 8th electrons. This is one node, so that counts. Then, how many other quarks are there? Well, we know how many atoms there are. We know every atom necessarily has so many protons and neutrons, so we can figure that out, and we can get a nice average of that. Just at this point, best you can do is kind of like, the best you can do is get an average. The best you can do is just estimate it this way, because we can't count all these things. But in principle, you can. This is the beauty of it. In principle, you can count all these things. But let's just say, on average, I think this is like how many hydrogen atoms there are in the universe. So let's just go with that. It's easy, right? One proton, one electron. It's 10 to the 80th, 10, whatever. So 10 to the 80th hydrogen atoms, let's say 10 to the 80th electrons. So 10 to the 8th superstrings that are electrons. And then, so consequently, then there's one superstring for every quark and 3 quarks for every baryon. And let's say then there's one baryon for every atom. This is actually even redundant. Okay, so let's just say that. Then let's say for every one atom. So let's say there's 10 to the 80th atoms. For every one atom, there's one proton, one baryon, which has 3 quarks. What is that? Up. Strange. I actually have to go over and remember all my particle charts. But okay, so you have then one baryon, 10 to the 80th baryons. You have the one electron that comes off of this, so it's 10 to the 80th electrons, which have 10 to the 80th strings, and you have 10 to the 80th baryons. Each one has 3 quarks, and so that's 3 times 10 to the 80th quarks, which have one string to each of those. So you have 3 times 10 to the 80th strings in this. And if the strings are the fundamental fabric of everything, well, then that's it. You're done. You only know the string, all the strings, and for every string there's one corresponding quark, but there's 3 quarks to every thing, so you can't go higher than that because that becomes a tree. So you can't count that, but you know this. We have 10 to the 80th strings for the electrons and 10 to the 80th strings for all the quarks, and 3 quarks for every 10 to the 80th baryons, or whatever the case may be. But you can't count those in the graph because it's a tree, and so you will color in this node, and then this node, and then this node, but that's it. So you know that. You have 1, 2, 3. Okay, fine. color in those, fine, but that's it. Color in these three, you can color in this, and then this, and then this, and then this, and that's it. That's it, you can't go any further. So then Z becomes 1, 2, 3, 4, 5, 6, 7. For every baryon, there are 7 nodes. 1, 2, 3, 4, 5, 6, 7. Can't go high. 8, maybe. But you see, you can get to this eventually. So you have 10 to the 80th, 10 to the 80th. This is a node, this is a node. There's going to be 10 to the 80th of those nodes. And so you have now a very countable number, at least as an estimate. Okay, whatever. So now you have 10 to the 80th superstrings that correspond to 10 to the 80th electrons, which correspond to 10 to the 80th atoms. You then have, what? 3 times 10 to the 80th superstrings that correspond to all of the quarks, 1-to-1 correspondence to all of the 3 to the 80th quarks that are counted as well. And then all the baryons, there's going to be 3 of those, so it's just going to be this number, we'll call that n, because there's always 3, it's divided by 3. So it just becomes 10 to the 80th. It's very simple. You can count upwards. Once you know all of the atoms, you can break it apart. Once you know the standard model and the structure of the standard model, you can count within a fair estimate. 10 to the 80th is a good estimate for the number of atoms in the universe. You can find a nice average, since most 90% of the atoms in the universe are hydrogen. You can get a damn good average of how many superstrings there are that comprise the universe. And there you have it. This, then, is the number of particulars in the universe. For the graph. That's all we care about. That's the number of nodes in the graph, I should say, that correspond to particulars in the universe, because you're never going to get to forms this way. So it doesn't even matter how many forms there are. You only need to know the superstring. You only need to know the particulars, because that's all you get. Because you get all these circles with the forms, because you have multiple particulars correspond to multiple forms, and multiple forms correspond to a single particular. You can have all these circles, but they won't serve you any good, because you can't find the zero forcing value of a cyclical graph. So, or you can, but it's 1. So it's pretty useless. You want to maximize Z. Well, we just did that by counting all of the superstrings and quarks and baryons. So, whatever this sum is, we'll call it, we'll call the number of nodes in the graph S for the number of stuff in the universe. And then the Z value is going to be, we'll call it G. I don't know, the God number. The number of, I don't know, there's a word for it. The number of free nodes or whatever. Zero forcible nodes. The number of zero forcible nodes in the galaxy or in the universe or something like this. I don't know. Actually, I can't do G because it's MSRG, whatever. N, big N? No. I don't know, what? Oh, I know. It's data. Okay, S and it's data. So this becomes S minus it's data. But that's the awesome bit, because this is a real number. We'll do 1, 2, 3, 4. This is going to be less than the number of nodes. Well, that'll be some big number, but a finite number, S. 4 minus 4 times 10 to the 80th for the 1, 2, 3, 4, 10 to the 80ths. Actually, do this. Plus 3 times 10 to the 80th. Plus 3e80. And that's that. Okay. Well, this is going to be about 6 times 10 to the 80th. Right, so we can just simplify. Well, all right, I'll keep that. I think that's right. All right, 3 380, there's just 2 of them. So this becomes what? S minus, I'm just going to get rid of this. It's driving me crazy. Okay, so we have S minus, yep, that's right. So we have S minus 4E80 plus, you can just add these together and you'll, right, yep, and you'll get the 6E80. Oh, look. I think that just happened to be the case, but actually I guess it probably isn't, but whatever. You get this. So your MSRG is that. So this number, the amount of stuff in the universe, is gonna be, within an order of magnitude the same as this number. So the zero force number is always gonna be kind of close to zero. I'm gonna guess 3. I'm gonna guess it's always gonna be greater than or equal to 3. I'm just gonna guess that. But you see, the S is a very countable number. This can be a very countable number. The number of nodes in the graph actually no, because S is gonna be the forms. Oh, and we forgot the 2 forms on top. Plus 2, sorry. So it's such a minuscule difference, it doesn't even matter at this point. But the number of nodes on the graph includes all of the forms. But the number of forms, there's going to be 1 form for every particular, at least, because every particular has to correspond to that same form. So there's going to be the form of superstring. All these strings are going to correspond to that 1 form. That's a problem, isn't it? Yeah, that's a problem. If they all correspond to the form of a string, it's a cyclical graph. That sucks. Well then. I mean, if it's a cyclical graph, then so be it. I don't know. I still think there's something here. I don't know what it is anymore, but I think there's still something here. Even if it is, then at the very least you get 1, 2, 3, and then for every quark there's a thing, so that'd be 4, 5. So you at least get a form for every level of stuff. So you get a form for strings, a form for quarks, a form for... Actually, that still kind of works. It's not what I kind of hoping to get, but it still kind of works. Because all of these corresponds to the form of a string, the form of a quark, well, fine, the form of a string, the form of a quark, the form of a baryon, and the form of an atom, which is fine. These are going to be, cyclical graphs. But that's okay, as long as you know this. Oh, so actually that helps. Looking at it this way, that's even better, because now it's actually entirely countable. It doesn't even matter how much stuff there is in the universe. It's actually entirely countable now. Atoms. Now it actually becomes a lot like Bunge's. It becomes a lot like Bunge's system of emergence. Strings, quarks, baryons, atoms, molecules. Actually, strings are energy. Then you get matter. Baryons, atoms, molecules. I guess life would be the next thing in Bunge's thing, etc. Or maybe, matter, maybe cells, and then life, etc. And then mind and all that. Okay. There's an interesting thing. So it could still work. So Bunge's levels correspond to the forms, which would be a part of the graph. There's an idea. Okay. So you have string, quark, baryon, atom, molecule, etc. That's fine. What you basically get is, well, just like this, all sorts of stuff. You get these cyclical things, S. So, okay, you color in S. That's fine. You can color in string. You can color in quark. So you still get this big number, but then you have to add in all the levels of emergence. The levels of emergence. So you still get all these things because you'll color in S. Oh, you'll color in string, absolutely. Strings also correspond to energy. But that'll be expressed, if you have string down here, then energy can be expressed out here like we had earlier when we're talking about all the different Union Jacks. So it'll be just expressed in a different dimension, but you'll still have form of string correspond to all the things, and you'll color in string, and you'll color in this, so you'll have energy, string, the strings themselves, but then that's it, because the strings are going to correspond to energy. So you color in energy, you color in strings, but that's it, because then now it branches off 3 ways. Okay, so you can't do that. So that's fine, but you color in then energy necessarily, string, you color in the strings themselves, and then you color in quark, the set of emergent levels. I call them, emergent levels. You'll color in the set of emergent levels, quark, baryon, atom, molecule, etc. And then that's it, because for every one, you're going to correspond necessarily to, they're going to branch off to at least 3 different ways. Fine. So you color that in, and this is colored in. But you can't color in this node because, or actually you would. Oh, that's fine. So you still get, yeah, that's what I was talking about. You still get this huge number plus all the emergent levels. Okay, so you actually, that's fine. So you would actually get the MSR of the graph is less than or equal to S minus minus zeta plus all of the emergent levels plus this big number. And I'm going to call that big number G. That big number we had, I'm going to call that G. Okay. I'm going to call it G. Whatever. Prime. Just not confuse it with that. Okay, I'm going to just do that. So all of the particular stuff in the universe, all of the emergent levels, and then zeta. Oh no, that is zeta. Never mind. Never mind. That number is zeta, right? So that's fine. You're going to color in zeta into all of the emergent levels. The emergent levels, and necessarily the basis of strings energy. So 1 plus, so 1, which corresponds to energy. All of the emergent levels, and energy is included. So then quarks, baryons, atoms, molecules, etc. Matter. Do we need matter? Plus, okay, fine. Energy and matter. What time is it? Oh, I have to keep going. Okay. 2 plus 2. So MSRG is less than or equal to S minus zeta plus emergent levels plus 2. I think.